Where's my... Alright, sound check, as usual. Alright, sound works. Hello everyone, welcome to the Vulkan stream, where we write a Vulkan renderer from scratch. Today we will do a bit of maintenance, clean up some validation errors, or rather all of the validation errors that were left last time, implement swapchain resize, and in general sort of prepare for the for being able to actually write like meaningful code that does interesting things, which we might get to this stream or we might get to next stream, I'm not sure. So I'm still streaming this from my old system. I did get some of the new components. They're like behind me. If I move away, you might be able to see them. So I'm still waiting for like half of them. They should arrive today, so maybe I'll have a chance to build the desktop today and then stream from it tomorrow. Until then, I noticed that whenever I start my Vulkan app, the stream freezes for some reason, and I don't really know why. I tried to switch the video encoder, maybe that'll help, maybe that won't help, but regardless we'll just kind of suffer through this. We won't look at a lot of stuff that we will render today, because it's still basically just a triangle, and I'm hoping that these issues will go away when I have a desktop. Meanwhile, interesting. Meanwhile, Visual Studio thinks that interesting. Yeah, so I just installed the new Vulkan SDK that adds support for some of the new NVIDIA stuff that we will be playing with at some point later on this stream. And somehow Visual Studio decided that it doesn't know where Vulkan H is anymore. So that's inconvenient. I don't know why. Let's try to fix this, because I kind of want IntelliSense to work. And then we'll just start working on this. Let me know if, so I enabled like hardware video encoder. Let me know if video on the stream is somehow weird, because I have never streamed with that before. Like if the quality is bad or whatever, I can switch back to software. Alright, so basically Visual Studio remembered the old path to Vulkan SDK in a bunch of temporary files, and this threw it off. Alright, so everything seems okay, that's good. Let's start. So let's recap where we were last time, and I want to try to add code to my main loop. To make sure that the window is redrawn only when there's a new event, new like mouse event or keyboard event or something that happens. In general, you don't do this in interactive applications, because if you want to display animation, this doesn't work, but I'm hoping that this will make it make the problem of video stream freezing when I open the window go away for the time being. So let's recap, where are we? So we have an app that we can run. Let's see if it still runs. Okay. There is a bunch of validation errors. So yeah, now you see I added this code, so now when I move the mouse the thing is redrawn and we get new validation errors. So that hopefully will fix the stream issues. So we have a bunch of validation errors, we should get rid of them to make sure that our code is validation clean. And then the other thing is, if I resize the window right now, you see it doesn't really work, so we should fix that. And then maybe we'll start drawing some meaningful stuff. Oh, there is a missing VK check macro here, so that's not good. Before we start doing that, you notice that right now there's validation errors, but our app doesn't, it happily runs, right? So this makes it easier to miss validation errors. So what I want to do is I want to fix this problem. The way you fix this problem in Vulkan is you register a debug callback. Now let's see if this works. So I wanna enable an extension that we haven't enabled yet, which is called debug report, I think. VK KHR. And this should make it possible to use the function called VK create debug report callback, which we can use to register a callback that the Vulkan SDK calls whenever there's a validation issue. And then we'll put an assertion there, and this means that whenever there's validation error, we will catch it immediately, right? So the way this works is that we will create this function, and I should have done this on the first stream, but I kind of consciously avoided fixing validation issues, so we'll just do it now. Callback VK debug report debug. So there's like a newer extension. I forget what it's called. VK create debug. Yeah, I think the new extension is called debug utils. I don't know if we should just use that. I don't know if I have this. Well, yeah, right. I should have it. Let's just do this first, and then maybe we'll switch to that extension. Yeah. So when you create this callback object, you have to specify a function pointer that will be called whenever there's a validation issue, or whenever there's anything that the validation layers want to tell you. And you also should specify flags that tell the validation layers what kind of callbacks you're interested in. And we'll just be subscribing for all of these for now, and we'll see what happens. All right, and then we need a callback. I guess I want to call it debug report callback. Why there are so many spaces here? All right, let's spend some time to reformat this code so that it looks nice. I'm like not a fan of vertical alignment. Oh, it didn't. Okay. I never can remember. So Vim has like a special, okay, yeah. Vim has special regular expressions, and I always have to alternate between Vim's regular expressions and like normal regular expression syntax. And I always mess it up. Alright, so that's our callback. And basically what we want to do is we want to, if it's an error, so this is debug report error bit ext. Oh, what is this? Debug report, okay. Then we want to assert. So I guess we'll just assert that. And we want to return, I don't know what we want to return. Let's open Vulkan spec and look at how this extension is supposed to work. So why does this link not work? Okay. Oh, maybe the browser hasn't loaded the full HTML file yet? No, it looks like it has. Programmable primitive. No, it definitely hasn't. Oh, it doesn't even open it further. It just decided to stop halfway through the spec. This is what happens when you have an HTML page that's like 8 megabytes of HTML. I should have opened the spec before the stream. Okay, now my browser is slow, so it's probably loaded. Let me double check. Which keyboard do I use? So I'll have to dig that out. I don't remember what the keyboard is, but I kind of bought a random. I had a befriend, I don't know. So I don't know if that's a thing. Yeah, that might be a thing. Yeah, so I use this keyboard. So when I had an incident on a stream like a few months ago where my keyboard died midstream, I got a new keyboard, and I just got like a random keyboard from Amazon. But this was a really lucky find because I really like this keyboard. It has really good feeling to it. Yeah, it sounds nice on stream. It's not like too loud, but it's not too quiet. I don't know. It feels good. My only regret is that it's white and everything else on my table is black, so that's a weird color. Well, except for my cup. But I guess I can at some point get a black version. But yeah, otherwise I like the keyboard a lot. It's a good keyboard. It's completely unexpected. I just got a random keyboard from Amazon and I happen to like it a lot. Alright, so so we have to specify callback. Let's see. The callback is called, the implementation does a bitwise and the callback will come. Dun dun dun. What should the callback return? The application should always return false. True is reserved for use in layer development. Alright. Why am I getting text on my phone? Alright. It's probably not important. So let's run our code and see what happens. Let me check what the deal is. Useless text. Useless text is useless. Oh no. I fear that this might be the case. So this is the point where we will, that's what I thought was gonna happen. Okay, so this is the point where we will slightly go against the rules that I set for the stream before. where I said that we will not use any Vulkan third-party code. The problem is that we are starting to use extensions. So we technically used extensions before to create the swap chain, but these extensions are kind of like really core to Vulkan. It's hard to use Vulkan without using these extensions. Now we are trying to use actual extensions, and I'm expecting that we'll use more extensions in the future, because remember, we want to experiment with like new RTX features and in general some features of Vulkan that you don't see covered in tutorials normally. So we'll have to use extensions. The problem with Vulkan SDK by default doesn't really come with an extension loader. So what you can do is you can load, and it's kind of interesting, they do have a prototype for this function apparently, but they don't. Let's actually double check if this is true, because it's kind of odd that they would have a prototype. Right, yeah. So basically, I mean, it's like an PDB file and in some random layer lib, but the Vulkan loader, the Vulkan like library that we are using doesn't expose these. So that's the problem, right? So what you're supposed to do when you write Vulkan code is you're supposed to say, okay, and let's actually do this first, but then I wanna actually switch to a library that will do this for us. So you're supposed to say whenever you need an extension, you need to load it dynamically. So let's just ls this using, it's already a pointer, debug report callback using a function called vk get instance proc adder, where you pass in an instance and you pass it a function name, which is this name, and then you can call this function, right? And this means that you are not linking to this function statically anymore, you're linking to it dynamically. All right, so this worked, and you will see that our assert fires, right? This is because we have validation errors. Now let's improve our validation callback a bit so that we actually know what the validation error is, right? So we'll be, okay, so let's first say that we need a better error message. We'll assert saying validation error encountered. And let's print the message. Let's just print the message for now. There's like other things here that you might want to be printing, but I just want to see what it looks like for now. Oh my. And now we get a lot of completely useless crap. That is not good. My guess would be that we don't need this debug bit. I don't know what it is. And do we need information? Information is probably also, well, let's see if this was informational messages or not. All right, yeah, these were, I mean, they print like the extensions that are available and things like this, but why do we care? All right, good. So let's see. So we have a message that tells us that we have a problem. And we don't know, so this is probably a warning, not an error. And this is probably an error. So let's see, let's say that we want to print the type first. And then the message. And the type is, there's flags that we have here. So let's just do this. So if flags have an error bit, then it will be error. Otherwise, these flags have I guess either warning bit, and then we'll say warning, and otherwise we'll say just info, and we shouldn't hit this right now, but this is like for the future. Yes, let's reform this code so that the structure is more apparent. Formatting ternary ifs is hard because there's like a lot of ways how this looks really weird. I usually do it sort of like this. Ah, wait. Yeah. So let's do this for now. Now we should, I think, see that the first thing is a warning. Yeah, so we get 2 warnings, and then we get an error, and then we assert. So this is good because now we kind of are forced to fix all errors at least, but we'll also fix all warnings before. Oh, this is okay. All right, fine. Yeah, before. What was I saying? All right, yeah, so this fixes us to fix all of the errors before our code actually runs, right? Which we didn't want to do last 2 times because we wanted to get something on screen, but today we want to clean this stuff up. So let's go through this one by one. So the first thing that is telling us is that we have this call to vk get physical device queue family properties. And remember, we are using this shortcut where we are saying, hey, you never need more than 64. And Vulkan SDK is telling us that you probably should get the count first. And I don't know if this is a useful warning. It doesn't seem particularly useful, but I kind of want it to be warning free. So so I guess what we'll do is we will get the count, and there was like an Intel bug that we ran with this thing last time, not with this function, with some other function. But okay, so the way you usually work with Vulkan is whenever you need to get an array out of Vulkan, you first get the number of items in this array, and then you get the actual items. So for now, let's just say that, oh, and I kind of want, I was talking about this before on stream, but I kind of just want an array size macro. So there is like a nice way to do this, but we'll just use a C way to do this. Yeah, because I kind of don't want to type all of these things all over again. So for now, let's not use so like in theory, if you get more than 64 queue families, then you probably need to do a dynamic allocation on heap. But this means we'll start using dynamic allocations everywhere, and that feels weird. So for now, let's just do it like this, right? It'll fix the warning, and then we might come back to this later. So we have this same, yeah, so we have the same warning basically for surface formats, and this is the Intel, this is where we hit an Intel bug last time, so I guess it's good that it forces us to do something slightly nicer. Should we just do 64 as well? Or, you know what, okay, alright. Since this is called a cleanup stream, let's just remove the shortcuts. Unfortunately, it needs dynamic allocations, but what can you do? So, we will say, for queue count, we will say, okay, fine, however many queues the device has, let's just retrieve all of them, and then this code can stay as is for now. And then let's do the same thing for this. I kind of didn't I mean, we'll probably use STL anyway at some point on the stream, and it's not like it's wrong to use STL necessarily. It has issues that I covered in my mesh optimizer stream, but it's, you know, it's fine. It's not terrible. What was the type? Surface format, KHR. Formats, and then formats data. The good news is that we'll work around the Intel bug that we have seen, so that's nice. Now, there was this thing, let me just fix this while we are here. I was talking about this on stream last time. Let me try to find this in the spec so that we can just handle this. But I need to find this in the spec first because it was like a weird corner case. Aha, yeah. So we are getting all of the formats that the device supports. In general, we kind of want to go through the list of formats and say that whenever we find a format that we like, we should return it. There's a special note in the spec that says that if there's just one supported format that says undefined, then you can use any format, which is actually nice for us, right? So we should say that format count should be more than 0. If not, then if not, this means you don't really support presentation. It might be invalid as per spec. It might be valid, I don't know, but I'm hoping it's invalid. So then if there's just one format and it's VK format undefined, then we can pick any format. We like this format, so let's just pick this format. Otherwise, we kind of can pick just the first format. Since this is a cleanup stream, I'm doing things right. To do things right, you should remember that in theory, the Surface, for example, can support presentation into 16-bit formats, 10-bit formats, and in general, like random formats that you might see, right? So what I kind of want to do is I kind of want to say that I want to go through a list of formats, and if the format is a 32-bit format, then I want to use that. And you might want to do something like first, and sure, let's do this. I don't like my monitor doesn't do this right now, but in theory there are monitors that support 10-10-10-2 format. And if I can find this in the I seem to have a hoarse throat today. Where is this? Oh, it starts with A. I see, right. So you might want to say that if there is a format that is VK format A2R10, I don't even know which one, whatever, it doesn't really matter. If there is a 10-10-10-2 format, then we kind of want to prefer this, because that will mean that the picture quality is better, assuming that there's like an HDR pipeline and we actually support this format correctly. And then failing that, so I guess in this case we might want to pick 10-10-2. So like you might sometimes want to do things like this, but for now we'll just say if there is a 32-bit format, prefer it. Otherwise, just return any format, just present to something. So if there is a device with only 16-bit presentation, if this is valid in Vulkan, then this code will also work. Alright, so we sort of fixed this code. Let's see what the next validation error is. Well, there was a build warning that told us that array size is already defined, I guess, in Microsoft Visual Studio, so that's nice. Alright, so before we create the swap chain, the validation layers want us to get the surface capabilities. This is important. I will cover this in a second. Let me just first see. Right, so Windows defines array size as well. So we'll just say that if in dev array size, we want an array size macro. Otherwise, we'll just use the system provided one. So when we create the swap chain, right now we are cutting a couple of corners. So we specify a color space Technically, we could get a color space from this function, but whatever. I will not bother doing this. I guess it's fine. If you do like HDR or something like this, then you might, yeah, like then you might have to use this value. Otherwise, it's probably fine. But the thing that we are sort of ignoring right now is a couple of things. The first thing is we select the present mode and hard-code it to FIFO. Now, FIFO should be supported by every Vulkan implementation. There are some cases where you might want to use another present mode, but in this case, you have to ask what modes are available. The other thing that's kind of more important is this composite alpha thing. Composite alpha says what should happen with the alpha channel of your swap chain when the image is presented. For example, you might want to say, hey, I want to use alpha as transparency, right? In which case the parts of the window or view or whatever your presentation system deals with will be transparent, translucent, right? We kind of say right now, hey, it just should be opaque. The problem is opaque isn't guaranteed to be supported. I think on Android, one of these is the only supported format or like composition method. So you have to ask what's possible to use on the swap chain, and to do this you have to get physical device swap chain surface capabilities. Oh, and you need a physical device for this. Right, that's fine. Let's do it like this. Alright. I don't know how to structure this code yet. Let's just do this first. Surface caps. Oops. And I guess let's just pass. Oh, yeah, so you can see that it tells us what it supports in terms of transform flags as well. Transform flags say what should happen when you present this. Should we rotate the image? Should we mirror the image? I'm kind of hoping that identity is always supported. What is not always supported is the transform. So we could just say that we should always use the current transform. Is that a thing? Let's see. Normally you should, if you think you know what transform you want, you should look at the bits that say which transforms are supported, and if some bits aren't supported, then you should do something with this. So let's see, so the current transform is, oh, not transform, sorry, I need support composite alpha, right? So this is 9. 9 is 1 and 8, right? So this says, no. Alright, so this says that we support opaque, which is what we are using, and we also support inherit. I don't know what inherit is, it probably doesn't matter much. However, remember, opaque is not guaranteed to be supported. We can look at if there's any guarantees, but I think there's no guarantees. I think there's probably a guarantee that at least one bit is supported, but I don't think there's a guarantee that kind of odd. Oh, right, yes. Right. So it says there will be at least one bit that you can use, but it doesn't say which bits can be used. And in practice on Android, you cannot use this. It's always either this or this or this, one of these three, one of the other three. So let us just alpha, composite alpha, composite well, let's just pass this guy there. Oops. It's technically a struct, so maybe I should pass it by constref, but who cares? I don't know of a nice way to write this code necessarily, so let's just brute force. We basically are saying, hey, we want, I mean, we can just do something like, we can just take the first bit that's set, but that's kind of obscure. So let's just say, hey, whatever is supported. Whatever is supported, we will return. Right. This will be a monster ternary if. I kind of blame Vulkan spec, and then we'll just say whatever. Let's just assume that if nothing is supported, then at least this thing is. This thing is weird because this, well, no, yeah. I kind of wish there was at least one value that was like guaranteed, because the only reason why this might matter is if you output alpha that's not 0 in the output alpha, then something may change. But the thing is, all of these three modes, they work exactly the same when alpha is 1. So if you output alpha 1 in the final frame buffer, it doesn't really matter. So I kind of wish there was some way to say I don't care really what happens as long as alpha of 1 is correct. But that's fine. The other thing that we might want to do is, I don't know if this min image count is valid to always set to 2, because I think what can happen is that in theory the min image count in this guy, right, so this has min and max image count, and this is the number of buffers that you have in the swap chain. So we are using double buffering, you might want to use triple buffering, quadruple buffering, I don't know why, but you know. We might need to use something like the max. Oh, what? All right, I guess let's just start using STL, because why not? And let's make sure that our windows, oh wow, these guys are very different. We should clean that up. Let's clean that up. But yeah, we should say that so we want like win32 lean and mean probably globally, so that our builds are faster. We want no min max because Windows H is weird. Yeah. So we also want this basically to be, what is it doing on Win32? All right. So what we want to say is that for all patterns, for all configurations, we want to set this. And then for debug, yes, instead of end debug, we want underscore debug. And I thought we said that we are going to use assertions in release. So why did we have an debug in the first place? Let's just do this for now. All right, so that hopefully will make yeah, that's fine. All right, so I'm kind of losing track. Oh, right, yes. So we did all of this so that stdmax actually works. So now let's say that we want a maximum of 2 and however many images the caps support by default. And this is a unit 32. So there's that. This might be good enough for now. Oh, we aren't actually using the surface composite value. So this might be good enough. This... What? Oh, composite alpha flag bits. Okay. Okay. So this might be good enough. You might want to tweak this code at some point. We might want to tweak this code at some point, like maybe you want to try to use triple buffering and a different presentation mode, like mailbox. We won't cover this right now. We might cover this at some point in the future. And this should be good enough, and this should silence the validation errors. I don't know if there's a better way to pick the correct composite value. It's kind of unfortunate that it's so long and scary. All right. It's kind of also, I kind of want to see the output here because whenever there's a debug issue, let me do that. All right. So this is the Intel. Well, like we were working around an Intel bug with the swap chains. But there's a warning that says it's the same thing. It says when you get images from the swap chain, you should first ask how many images are there and then get them, right? So we should do that. Before we do that, we should... Okay, let's do this. Like... This is the point where I'll have to look at snprintf docs to figure out if this code is even correct. But I thought in C99 snprintf is sane finally, so it should be fine. And then we want to printf, and then we want to output this to Windows console. Technically our code only works for Windows, but if anybody wants to run this code on Linux, maybe it will be slightly easier for them to have the code at least try to compile. Alright, so now we have this these errors both here and here, which is nice. This means that whenever we break into a debugger, we immediately see the information that we need. Alright, so yeah, so let's fix the warning first. So this is the point where we remove this hack sort of about the images, where we currently assume that it's always 16, but okay, fine. So the correct way to do this is you ask how many images are there in the swap chain, and then you're like, okay, cool, let me just use std vectors like it's nobody's business, and that's a heap allocation, but who cares? There's not, it's like it's done very infrequently. Alright, now we support more than 16 swap chain images. If you ever have a device that has more than 16, which is gonna be impossible, then you should be happy. Alright, so now we can focus on the error. This is the only hard thing that we are doing today, probably. Well, at least while we are fixing validation errors, this is like the only hard thing. So let's look at the message. The message says that we are trying to submit a command buffer using an image, which is our swap chain image. And it has a layout undefined, but it's used as attachment optimal. So let's, oh yeah, it doesn't. So let me go over the pipeline barriers, because fixing this validation error requires the use of pipeline barriers, which we have not talked about on stream yet. So in Vulkan, there is two kind of important things that you should know about every image resource. And one of these things applies to buffer resources, and one of these things is image specific. So the first thing is called image layout. And very roughly, this represents the way in which the image data is stored in GPU memory. But of course, this is an abstract enum because like Vulkan can depend on the specifics of every GPU, right? So this tells us something about an image in an abstract way that may, on a specific GPU, influence how the image is stored in memory. For example, there are values of this like color attachment optimal. This means that it's a way to store the image that is fastest on the specific GPU to render to using a frame buffer attachment, which is what we are doing, right? And Vulkan spec says that when you render to a frame buffer, all of the attachments that you output color to have to be either in this layout or there's a special layout called general, which basically says, hey, you can do anything with an image, more or less, it doesn't really matter, we don't care. It also might be the slowest path on this GPU, right? There's some specifics that depend on the hardware. Color attachment optimal images may, for example, support color compression transparently, where a GPU would look at, for example, a quad of like 2x2 pixels and say, hey, these colors are basically the same or really close. Let me losslessly compress this by storing one of these colors and then deltas, or just one of these colors and the mask that says all of these are the same, or things like this, right? This is important for optimizing GPU bandwidth. But the GPU has to know that the format that we are using is this, because there is also an image layout called shader read optimal, which basically says, hey, here's the image format or like image storage format, right? That is fastest for the shader to read, for a shader stage to read. And what can happen is that when GPU supports color compression, the texture unit in the shader doesn't. This means that when you render to a texture, you use color compression by virtue of using color attachment optimal layout. And then when you start reading from it in the shader, two things have to happen. First, you have to tell, well, it's basically like one thing has to happen. The texture unit cannot read this data, so you have to decompress the image, right? You have to undo this compression that you were using for performance sake, and the driver has to know that you should do that. So in Vulkan, when you switch image layouts, and in Vulkan you can render to an image in color attachment optimal format, but not in shader read optimal. And you can read from the shader with shader read optimal, but not with color attachment optimal. So this means that in Vulkan, basically, either you always use general, because it's compatible with like everything, but this is super not recommended on some of the current GPUs, not on all of the current GPUs. Some GPUs don't really care. On some GPUs, it will be substantially slower if you always go through general. Or you have to use the correct image layout, which is of course the recommended way, but then you have to transition the image between layouts as the usage changes. So we are not reading from our image in the shader right now, but what we do is we do present. So there is like a layout called present src something. And this is the layout that has to be used when you present the image to the window or to the surface. Because once again, the presentation engine may not support texture compression, image compression, color compression, or whatever else you might want to use, right? And there's like a few others, like there's depth, stencil, optimal, etc. Right? So there's like a few image layouts. When you create an image, in general, the image starts in a special image layout called undefined. This means we don't know really what the image contains. And we don't know what data, like what format the data is stored in, because like it's all completely undefined, right? We just created it, there's nothing there. What should happen is that before you use an image, you have to move it to the image layout that you think is necessary. For example, in our case, our swapchain images start in undefined. We have to transition them to color attachment optimal. When you do a transition from undefined to color attachment optimal, the contents of the image gets lost. But we don't care because we are rendering to the image, right? So that's the first big thing that has to happen. The second big thing that has to happen that you have to be aware of, is what's called access. Let's call this access metadata. And this is basically saying which stages of the pipeline do what kind of operations to your image. For example, when you're reading from the shader, when you're reading the image from the shader, you're using the shader stage, say fragment stage, and you're performing an operation called shader read, right? Not surprising. When you're rendering to an image, you're using a stage called like color attachment output, and you're using an operation called, I don't remember what it's called, but like let's just call it write pixels. This is definitely not what it's called, but let's just call it write pixels, right? In the same fashion, when like I was talking about image layout, I was saying, hey, you have to let the driver know that the image was color attachment optimal and it now is shader read optimal, to read from the shader. You have to tell the driver, hey, this image was had pixels written from the color attachment output stage, and now in the fragment stage we will start reading these data from the shader. So both the image layout transitions and changes to this sort of access metadata is not the official term, I don't remember if there is an official term, are communicated to the driver in the form of a pipeline bearer. So you say, the pipeline bearer says this resource was an image layout color attachment optimal and now it should be shader read optimal. Also, it used to be written from the color attachment output stage and now it's being read from the fragment shader stage. So the image layout transitions are useful because the driver may need to decompress, right? So it's a really heavy operation that might happen. The access metadata changes are necessary in pipeline bearer for a bit of a different reason. And this is because A, there might be caches on the GPU that are not coherent between stages that you have to flush. And B, there might be synchronization that has to happen between execution stages. So let me describe how both of these are might be important, and I will use the same example, the same simple example, the thing that every single renderer from OpenGL like 2.0, right, does, which is I will render to texture and I will use this texture in the fragment shader stage. So, so let's say there's a render pass, and then it renders to texture, right? And then there's like a pass that reads texture from the fragment shader. So two things might happen on a specific GPU. First, the rendering operation, the operation that actually writes pixels to the output, generally runs in a stage called drop. It's like render operation processing, I guess. This is the stage that does blending and color format conversion, like your shader outputs a floating point 32-bit value, but your target format is like RGB 8 unorm sRGB, things like that, right? This is a separate unit on the GPU. It has complicated behavior, it has complicated caches, etc. The texture unit generally uses a cache also to read the data. So, for example, there might be an L1 texture cache, there might be an L2 texture cache. the ROP unit may have a completely separate cache hierarchy that, like some sort of like tile cache, which is a bit different from the tilers, but whatever. So what might happen is that if you don't flush the tile cache before starting to read the texture in the fragment shader, some of the pixels may not even be in main memory, they may be in tile cache. So when you do this kind of transition, like here, right, something has to happen. So the first thing that has to happen is flush tile cache. The second thing that has to happen is invalidate texture cache. The reason why this is important is if the texture cache has stale entries in it for the pixels that were previously read from the same region of data in memory, if you don't invalidate the cache doesn't automatically know when pixels are written to the main memory by some other unit like ROP, it doesn't automatically know to invalidate itself. So basically there is no real cache coherency on the GPU in many cases. On some GPUs, some units are coherent, on some units aren't. Maybe some units on some GPUs are, like maybe on some GPUs every single unit has like coherent access through the same cache hierarchy and it all works beautifully without issues. But it's not super common. So this is the first thing that has to happen, right? You have to flush the ROP cache, roughly speaking, and you have to invalidate the texture cache. Now, on some GPUs, things might not be that bad. For example, on some GPUs, maybe the L1 cache has to be invalidated, but on some GPUs, ROP might be tightly connected to the L2 texture cache. So you don't have to invalidate L2, you don't have to flush ROP, you just need to invalidate the L1 texture cache, which is really tiny, generally speaking, and then just go. So that's the first thing. The second thing that has to happen is we need to wait, we need to essentially delay fragment work until writes complete. And this is what a lot of people don't realize. A lot of people have a conceptual model of a GPU where every single draw call runs on a GPU serially. Whereas, like inside the draw call, you may think, hey, obviously I run the work to shade the pixels, to shade the vertices, etc., to rasterize the pixels in parallel within one draw call. But a lot of people think that between draw calls there is no parallelism in the GPU. This is super not true. All modern GPUs have a lot of parallelism between draw calls. So what could happen is that if you don't delay the fragment work, what could happen is that you have a bunch of, so this is your GPU timeline, right? And then this is like render to texture. And it could be that the command processor of the GPU starts the draw call that reads from the texture like here, and then it ends here. What you do want is you want to wait, right, for the render to texture operations for all of them, for fragment shading, color rights, etc., to complete before starting this work. This does not happen automatically. It's important that it doesn't happen automatically, because turns out that if you just disable this, then the GPUs can run way less efficiently. I don't know the numbers off the top of my head, but I would not be surprised if the modern games would be rendered like 4 or 5 more than 4 times slower. Could be 10. It could be a substantial penalty. Because it's important when, for example, you have a draw call that only draws like 100 pixels on screen, it's important to not have to wait for these 100 pixels to complete before starting the next draw call with 100 more pixels, because otherwise your GPU is just not utilized well. The other thing that might be important is that in our case, remember, we are reading the texture from the fragment stage, not from the vertex. It's possible to read the shader, the texture from the vertex shader, but we are only reading this from the fragment shader in this example. So what the GPU can do, and this is completely valid, is it can say, I will start, if we have this barrier put in that says, please wait for fragment work to start until writes to the color complete. What could happen is that the GPU still starts to draw us earlier, and then there is like vertex shader that runs in parallel with rendering to a texture, because there's no conflicts on data, you don't have to wait. But then it delays the fragment shader work up until the render to texture actually completes. This does happen on modern desktop GPUs as well. It's really critical that this happens on mobile GPUs. On mobile GPUs, there is like a tiled architecture. It has certain expectations about like parallelism between different stages and things like that. And on tilers, it's like really critical that you don't just wait for everything to, like, you can't put a barrier that says I want to finish all my work that I'm doing now and then I want to start all of the work from this draw call. On tiler, this might be a bad idea, or a really bad idea. It depends on how much geometry you render, it depends on a bunch of factors, but it might be a bad idea. An example of when it might be a really bad idea is that, say this texture was a shadow map. So say you have really simple render with a shadow map where you have your shadow pass, and then you have your actual like scene pass. Right, so shadow pass renders a bunch of draw calls that go into the shadow map, scene pass reads all that, and reads the shadow map, right, and then just draws pixels on screen. Your mental model might be that it's fine, let's say there's a full barrier here, it's fine because, sure, we will wait for the vertex work to start, but vertex work goes in parallel with the fragment work, and things nicely interleave, and it's not a big problem. Tilers really want to do something like this. So there's the shadow vertex work, right? And then once that completes, they do bint rasterization, triangle classification, etc. Then they start shadow rasterization, and then they start like pixel shader work. And there's like not that much work in the rasterization and pixel shader for the shadow pass, right? Tilers really want to say also, like here, maybe even here, but this would rarely happen, so commonly it would be like here somewhere, potentially. We will start scene vertex work. And then when it completes, we will do the actual scene rasterization plus pixel shader or fragment shader. So tilers really want to sort of do the vertex work for a pass well in advance, because they have to do the vertex work for the entire scene. So if you have like a million triangles in a single render pass, a lot of tilers would want to do a lot of vertex processing, if not all of the vertex processing, for the entire pass before starting any work on fragment shading. So it's really important when you specify Vulkan pipeline barriers that A, you are correct. Because if there's no pipeline barrier here, then this code might not work on some GPUs. Like our code right now works perfectly fine, but it could be that on some GPUs it doesn't, because there is not a single pipeline barrier. B, they have to be, I guess correct is an ambiguous term, right? Correct describes everything that the pipeline barrier has to be. So they have to be sufficient, which means they specify all of the necessary conditions for all of the GPUs current and future to work with your code. And B, they have to be minimal, which means that, or like optimal, right? Which means that if you are reading from the texture in the fragment stage, you should not tell the Vulkan driver, hey, I might be reading from the texture in the vertex stage, because that will introduce unnecessary synchronization, which in some cases is really bad performance. Yeah, so that's kind of an overview. There is a bit of information about this in the Vulkan spec. There are some articles about this, although some of them are somewhat misleading. I also tried to cover this in a bit more detail in an article that I submitted to GPU Zen 2, which should be available at some point next year. But this is like the most complex part of Vulkan. How to correctly specify the barriers, how to specify them both sufficiently and optimally, how to do this without a lot of CPU or GPU overhead. There's other things here. For example, if you want to do 10 pipeline barriers, you really should just do one barrier where you tell the driver about all 10 resources. If you are doing really some of the compute stuff, and if you are in general going deeper into making GPU run really fast with full utilization or as much as possible, there's a thing called split barriers in Vulkan, which we will not cover right now. Maybe we'll cover it later at some point. But this is like a complex, deep topic. Also, there is no validation for this. There is validation, thankfully, for the image layout transitions, which is what we are hitting right now. There is no validation for this stuff. And this stuff is the thing that is hard to get right. Like, image layouts are easy to get right, there's validation, plus it's a simple concept. Access metadata is hard to get right. So, no promises that the code that we will be writing will get any of this right. If there's ever a validation layer release, please let there be a validation layer release that actually checks this. Then basically what I'm expecting is every single Vulkan program out there is just invalid, and then everybody has to fix their code for the code to become correct. So that's the intro, and now we'll start actually writing this code, and let me look at chat. Let me look at chat. Chat doesn't seem to care, so let's just go and do the things that we need to do for our code to be correct. So in our case, thankfully for now, the structure is really simple. We have an image, we have a swapchain image, and we need to render to a swapchain image, and then we need to present. Right, so when we render, the layout has to be color attachment optimal. When we present, the layout has to be present source. And then we have to transition between them back and forth. And things should work. And this should be the last validation error that we are hitting. I wanted to do one more thing to clean up this code, and then we'll do swapchain resize and stuff. Let me put a to-do quickly before I forget, because I remembered after last stream that there is a correct way to do this. All right. So yeah, so when we specify pipeline barrier, and I kind of want a helper function for this, but it's not going to be a very good helper function, but that's fine. So I kind of want a helper function that says pipeline barrier image, that given a command buffer and given an image, transitions the image from a layout to a layout and specifies the access masks and stuff. This is not a great function, because normally you should do many transitions at once. But in our case, I'm expecting that we won't really have many images to begin with. This might be the only image that we have for the foreseeable future, so it's fine. But this is not a great interface, but this will help us to simplify the code. So there's your trade-off. And I don't really remember what I want to call these parameters the same thing. It's like a slightly simpler interface to the pipeline barrier function in Vulkan. That's what it is. So let's look at what you have to specify. So there's two stage masks that you have to specify. This is the thing I was talking about. Like if you're writing from if you're reading from a shader stage in the fragment shader, you have to say that the stage mask that this image will be used in is a fragment shader stage. So let's do that. So vk pipeline stage flags c stage mask, and I also want here to specify vk memory access, I think it's called, or vk pipeline access, pipeline memory. Okay, you know what? We'll find out what the enum is called. So now there's dependency flags which we will ignore, and then there's for each image, this is what we need basically. Oh, and we'll need, yeah. Oops. So these are the access bits that I was talking about. Like on the fragment shader stage, you can read, you can write. For example, if you have a what's it called in Direct 3D, it's called an ordered access view. I forget what it's called in Vulkan, but basically you can just do random writes from fragment shaders to random images these days. So this could be right. And I kind of want to order these like this, so that we first say, oh, it was called vk access flags. So we first say what stage was doing what with the image, and I guess we'll say what the image layout was. And then we'll say the same things for what happens after. Right, so there's that. All right. And so this is just a super simple helper function that just makes it easier for us to tell the Vulkan driver what's going on with one image. If you want to call this function twice, instead what you should be doing is you should be calling this function once and then passing it a bunch of different structures. I'm almost wondering if instead it would be a better form to just have a helper that creates this guy. You know what? Yeah, instead of showing you things that I'm saying are a wrong thing to do, let's just have a helper function that creates an image memory barrier from an image, and then alright, yeah, this is just a dummy thing that just fills the struct so that it's less painful for us to deal with this, and then we'll just use it manually. It's gonna be fine. Yeah, this is nicer because this means that I can reuse this function in code that has to do 2 barriers at a time. So yeah, basically this is just gonna fill this guy. Alright. So we have to say that we are transitioning from source access mask to DST access mask from one layout. Should we just order them? Alright, fine. Let's just have a consistent order here. So in complex cases, you may want to say something like this. I am rendering to this texture, to this image on a graphics queue. But then I want to run an asynchronous compute job that takes this image and does some compute shader, runs some compute shader on it. In which case you have to do an image bearer that says, hey, I want to like sort of, I was working on this image on this queue and I want to start working on this image on that other queue. Thankfully we aren't using that stuff yet, and I don't know if we will. We will see. And there is a thing that you can pass for cases like this, which is vkq family index, vkq family ignored, which is -1. So let's do that. And this basically says nothing, like a cross queue operation does not happen. So then you want to give an image, and then you want to say, hey, what parts of the image are you transitioning? Because an image may have 5 MIP levels, and each MIP level is an individual region of memory, so individual synchronization rules can apply to an individual MIP level. And same thing happens for the texture arrays. So for now, we'll just assume that we are only gonna image, what's it called? Oh God. Sub-resource range. So let's assume for now, this is like a bad assumption because we'll have to break this assumption, but that's fine for now. So let's assume for now that we don't have depth. We will have to start using depth buffer, obviously. And let's assume that we just need, there is a special magic constant that I forget how it's called. Let's just say that we are transitioning all like the entire image, all MIP levels, all array layers, everything. Warning, not sure if people watching the stream will care, but there's a bug on Android where some Android drivers don't support these constants. So they violate the spec, they don't support these constants, but we are not gonna care, because remember, this is not like a stream where we write a renderer with Vulkan for like Android. Our code will not work on Android, and we will not make any attempts to try to make it work on Android. Alright, so we added a helper function, now let's just use it. So what should happen is that before we start the pass, we are rendering to an image, which is swapchain images image index. So what we should say, so remember the layout error was that the image started as an undefined. So what we should say is that we want to transition this image. Wow. I haven't really explained this bit, but okay, just trust me that this code maybe works fine. I don't actually know if this code works fine because there's no validation, and you know, we will look at this spec in a bit because there's one specific thing that I kind of wanted to clarify. But basically, okay, so what we are saying is, just ignore this for a moment. We are saying that the image will be used in the color attachment output stage, and then, oh, I wonder, can I do, is C++, well, let's test, oh, this is Microsoft Visual Studio. Alright, so we only want one image bearer. I'm kind of wondering if I can do like this. I don't think I can, but let's see. Oh, in Microsoft Visual Studio I think I can, but I think it is not. I think it still isn't valid C++, which is unfortunate a bit. But okay, so we might wanna, you know what? That's fine. We want a variable anyway. VK image bearer. No. VK image memory barrier. So this will be like render begin barrier. So we want a barrier that I will need to look at spec. This stuff is hard. Let's just I don't think I need an access mask here because, all right. The important thing is that we are now using color attachment rights, and then the image was in some layout that we don't care about, which I said was undefined, and then we want the layout to become color attachment optimal, which is how you should render images. See, a 1080p screen is like optimal for Vulkan, because if you don't have a 1080p screen, most things don't fit in one line anyway. Alright, the other thing that we want is that after we have rendered, which there will be a validation error about, but let's just anticipate it and fix it. We want to say that we used to do color attachment rights, and now we want to do presentation. It's probably, is it just memory read? Oh yeah, there's like no pipeline stage for this. Oh, I don't know how to write this code. Alright, so we are transitioning from the image layout attachment optimal to image layout present src, because we are going to be presenting an image. When we do so, we want to do a synchronization between the color attachment output stage, because that's what we were using to like to write these pixels, and it should be between, I think it should just be between pipeline stage top of pipe, but I'm not sure about this. It might be something else. We will look at this. So it was right, color attachment, and now it should be 0, present src, and top of pipe, and yeah. Alright, I don't know if it works. My guess is it doesn't, because there's no way this code, I mean it might, yeah, okay. So we are validation free, validation clean I should have said. My guess is our code is wrong. Because this is, so access masks are complicated. There is a super complicated thing about the access masks around this specifically. But let's fix all of the validation errors, and then, oh, I wanted to do, oh yeah, we can do swapchain resize, I think, in the time that we have left, that's fine. So the other thing that we need to fix is that we have memory leaks, because we are not destroying anything at all. Thankfully, the validation layer is nice enough to tell us that we aren't destroying objects. It tells us the type of the object, like vk debug report object type is the callback that we have created for debug stuff. So we should fix that. So let's fix that. It's unfortunate that... Alright. Okay. So the way we will destroy this is we'll just go over everything that we have ever created here. It's gonna be tough. Like this. We are destroying an instance, which is very noble of us, but... And then we'll just go over this stuff in reverse and then just destroy things. So we are destroying an instance, so we need to destroy debug callback. To do this, we do destroy debug report callback instance debug callback 0. This is this part where, okay, this is an extension. For now, let's just do manual loading. This is why you need an extension loader, and I think we'll switch to an extension loader because it's just obnoxious. So we haven't created anything here. We haven't really created anything here. You can't like destroy a physical device, I don't think. Yeah. So this object is, the memory for this object is managed by the instance itself. We have absolutely created a device, so let's do destroy device. Device. We are destroying a window like here, so that's fine. So we need to destroy the surface. Instance surface. This does not create anything, does not create anything, does not create anything. So we have created a swap chain, so we need to destroy that. The swap chain owns images, but we still need to destroy the frame buffers that we are creating, I think. So we've created 2 semaphores, so let's destroy that. So release, acquire. Well, it should be like this. It doesn't really matter which order you delete things in Vulkan, but at least I don't think so. But I'm trying to be consistent and destroy them in reverse order. Render pass. Shader modules. We don't technically need the shader modules for the entire program's duration, but it's fine. Oh, you know what? One thing that we should do here is we need to wait for everything pending on device to complete. We are technically doing this at the end of the loop, but this at some point will go away, and this should stay here. Alright, so we have destroyed the shader modules. We don't have a pipeline cache. I wonder if we'll forget to destroy it once we use one. It's fine. So destroy pipeline layout. Triangle layout. Destroy pipeline object. We are close. So these images are owned by the swap chain. We don't need to touch these, but these things we have created ourselves. Essentially everything that we have created, we should destroy. So vk destroy frame buffer, device swap chain frame buffers, vk destroy image view. Wait, what should happen here? Alright, are we done? No. Command, we don't need to destroy command buffer because that's allocated out of a pool, but we do need to destroy command pool. Alright, vk destroy command pool, device command pool 0. Alright, we're done. Well, not quite done, but so this is a hello world in Vulkan, right? We basically haven't cut corners. There is a small corner that we've cut that we should fix, and also we are relying on Vulkan 1.1. But the thing is, we could have used Vulkan 1.0. We are only using one tiny thing from Vulkan 1.1 to flip the triangle. So this is basically what a hello world in Vulkan looks like. This comment is stupid. We are using glfw to create a window, so that's slightly cheating. But thing is, you can create a window in Windows in like one line of code. Not a lot of people know that. So that's like, yeah, 600 lines for a triangle. So that's how verbose Vulkan is. But the good news is we have a foundation. Oh, we don't resize the swap chain yet, I guess. But we have a foundation for future stuff that we might want to do. Alright, so let's quickly fix a few remaining things that I wanted to fix. Let me look at chat. Chat is silent. So the one thing that I kind of talked around last time was that you might have 5 GPUs in your system, and 3 of them might not support rendering to anything, because maybe it's not plugged into the monitor, and also it's not like SLI'd into your main display card, and maybe it's just a compute device, that's some PCI Express machine learning module, and God knows what happens. And we're kind of ignoring this right now. So what we should do is this. We have this function that says, hey, do you have a graphics queue? So the first thing that we should do is that we'll teach this function to return us -1 when there's just no graphics support on the physical device. Here we'll say that family index should we just use vkq family ignored? Let's use vkq family ignored. It's slightly nicer than using, yeah. It's slightly weird, I guess, to return this, but it's fine, whatever. I don't care. So when we go through the devices and we pick the right one, we have one device right now. If my computer parts arrive today, if I manage to assemble them today, if I manage to not screw anything up and my computer doesn't explode and it actually posts and boots and I can install Windows, this is like a lot of ifs, because the last time I have personally built a computer, the last time, this happened, I want to say this happened 15 years ago, okay? I think that's about right. I have used a pre-built desktop after this for a few years and swapped out parts. I'm like capable of swapping parts out. That I'm really good at. But I think the last time I have built a computer was at least... Oh, you know what? Oh, I might be lying. Oh, no. I have never built a computer from scratch. I don't think this ever happened. I mean, I've like replaced every single component except for the motherboard in every single computer that I have owned from time to time, right? But I have never built a computer from scratch, ever. So yeah, I take this back. The computer that I was thinking of is, I think I bought a pre-built like 15 or more years ago and then swapped some things out over time, and then it became like a new computer. But if that works, then we'll actually have 2 physical devices tomorrow, because the computer that I will be building, it does have an integrated GPU, and it also has an NVIDIA RTX card, or it will, right? So we will actually be able to meaningfully debug this code, but right now there is only 1 physical device. Anyway, what should happen is this. What should happen is that we should not pick devices that don't support graphics, obviously, and we should not pick devices that don't support presentation. So let's make a helper function called supports presentation, vk physical device. So unfortunately this function has to be platform specific, because there's a thing on Windows called vk-get physical device win30, aha, this guy, which returns you a boolean, right? Graphics, what am I calling it there? Family index. Oops. Graphics family. Is that a better name? Seems like a better name to me. Oh, but then I have to, okay. You know what, that's fine. Let's just call it family index. So yeah, this is a function that is not available in Core Vulkan. It unfortunately, for some platforms, there is a platform specific way to answer this question. So, oops. If anybody ever ports it to Linux, this will be one more thing they'll need to fix. Well, should we just assume? Let's just assume true, because seriously, I don't know. But yeah, this is the correct thing to do. So the correct thing to do is that when you're going through devices, you have to just ignore the ones that that you can't use. And the way we will structure this code is like this. So we'll have a discrete device and a fallback device. We'll go through all physical devices, and then we'll say, okay, family index is get q get graphics family graphics. Should just get graphics family index. All right. So let's get the index. If it's vkq family ignored, then we'll just not use this device at all. If which would mean it's compute only, does not support rasterization. So then if our device family index doesn't support presentation, we'll also not use this. And then we will say if there is not a discrete GPU yet, then we will, and you know, we found one, then we'll prefer this one. Discrete. Let's do this. If there is no fallback, then we need one device, right, that works. So there's that. And then at the end of this, we will say that we'll just return if there is a discrete GPU found, we'll return that, otherwise we'll return a fallback, and then if nothing is there, then we'll return 0, and then this will be like a really critical assert, right? So here we might want to say, hey, if this wasn't found, just print something and just return, right? So like if you wanted to make this code nicer, we would say that like here we would say if instance isn't found, print an error return, and here we would say if device isn't found, print an error return. Which, you know, nah. If not, if not fallback essentially. Let's just keep it like this for now. So this should pick the correct GPU that, you know, we actually support. So let's do this. Okay, physical device result. If result, else, well, yeah. Then we'll just say that we have selected GPU. All right. All right. So there's only one GPU. We have selected this one GPU, but our code now should handle weird cases as well, hopefully. So that is done. Yeah, so we're basically done with the cleanup. Oh, almost. There's one other thing that I wanted to do. Damn it, and then I also wanted swapchain resizing. Let's try to get there. I don't know if we'll get there. One other thing I wanted to do is I wanted to start compiling shaders from Visual Studio. Because remember last stream we were like, hey, we need this code to run. Let's just build these PRV versions, the binary versions of the shaders manually. But like I want to start compiling this code in Visual Studio, because the hope is in Visual Studio you get syntax highlighting, which of course you don't. But let's see if that can be fixed by installing like a Visual Studio extension or something. Error tagging with squiggles and an error list. Generate. Oh, this is an interesting extension. Oh, hey, Sasha Williams published an extension. It has a rating 3, and this one has. Yeah, so this might do more to us than syntax highlighting, but I kind of just want syntax highlighting. I'll have to restart Visual Studio to get it. Let's do this separately. So right now I just edit the shaders to my project file, and of course nothing happens to them, right? But what you can do, what you should be able to do in Visual Studio, I have not done this before, is you should be able to, to say that you want to build them with a custom build tool. And then you should be able to specify properties of this custom build tool. And this will be really painful to deal with when we add GLSL files. So there's that. Can I, if I just specify it here, will it work? Let's try this. So what we need to do is we need to do in Vulkan SDK, in bin folder, there's GLSlang validator. I super don't know how that works. Let's see. Is there like item name? No. Let's Google how this works. I have never done this, ever. Custom build tool command line. Oh, this is different. Oh yeah, so this is what I was looking at. This is what I was looking at. So I want this thing to say that it should get the full path to the source file, the GLSL file, and then use Vulkan mode, and then output this to the build folder, which I don't know where it is. How does it like build dir, output dir, target output? I don't know. Help me out here, Visual Studio. Intermediate. I don't want intermediate. I want like final. Well, let's see. Hold on. Yeah, I want output directory. I don't want intermediate directory. Oh, and it lost. No, it. Yes. All right. Great. All right. So percent file name dash v dash. Oh no, wait. This was full path. Let's just say it's output directory. I don't remember what it is. Percent file name dot spv, and then the outputs are essentially this thing, and then the dependencies are essentially this thing. And then we can build it in parallel, and then I have no idea if this worked. Oh, did I? So both of these files should be built with this beautiful custom tool that we may have created or may have not created. Haha! well, it didn't work because my command, of course, it is not correct, because it's not. Let's try to figure out, instead of the output directory, how is this thing called? Output path, not output directory. Output path. All right. That did not help at all. All right, what if I just say, write it to the, what's the current folder here? So it built this, where did it build it to? Right, so this is not too bad, except that I'd want to do this in, well, how are we loading these shaders right now? Just from the shaders folder. Yeah, so we're assuming that, let's just save them in shaders folder for now, like essentially where we have checked these guys in, and then we'll deal with that later. Shaders. I mean, we can, yeah, okay. All right, let's see. So in theory, we can delete these PRV files. Oops. Git rm, and then we can add these guys to git ignore, and then we can do build, and it builds our two shaders. We can do build again, it builds our two shaders again. Damn it, that's not what I thought would happen. Oh, additional, is that? Wow. I mean, it's not terrible because they built really quickly, but it's also not great because I was hoping that it wouldn't. Why does... Oh, because my outputs are wrong. Sorry, okay. It's my fault. It's all my fault. And yeah, I guess I do need to specify this, probably. Alright, so if we don't change the shaders, nothing changes. Let's try to change the shader. Let's say, hey, I want the triangle to be, oh, and like, let's run the program. So here's our triangle. So now I want a different vertex position. It built the shader, it built the triangle. I mean, it changed the triangle. And then let's make an error. Let's build the project. Okay, the only issue is if I double click on these guys, it doesn't bring me to the compilation error. This is because GLSlang validator uses a different format for error messages. I wonder if there is a way to ask it to give me a Visual Studio compatible error message thingy, because that would be nice. It might not be a thing, because maybe they haven't thought about this. Well, it would be kind of weird if they haven't, but yeah, it doesn't look like there's a way to do that. We might file a feature request to Kronos. Oh, the other thing, no, yeah, there's no other option really. Yeah, there is another option. There's this GLSLC, which is similar to GLSlang validator. Maybe we should start using that. But I haven't used this guy before, so I don't know how that works. But maybe we should use that. GLSLC is, I think, Google's project that's called like ShaderC. That should be a nicer way to, like a more friendly, you know, command line that matches GCC better, stuff like this. But like, I don't know if it supports our convention with file name extensions and stuff like that, but maybe it does. So let's try and see if that works. I don't know, I don't see anything about I mean, this might not help us because the only reason why we don't like GLSlang validator is it doesn't, the error messages are not in a nice format. Let's see what happens if I just run this. Yeah, so it wants me to specify F shader stage, which I can't do in my beautiful custom build tool. So that's not cool. So I can't really use this guy. Yeah. So either way, even if that worked, let's see what happens if shader stage vert. Come on. Really? Oh, a head. Oh. Wow. Oh. Oh. Yeah, so this is also not Visual Studio format. So it doesn't even help. It wouldn't even help. So it looks like we need to file a GLSlang feature request to have a command line option to do like a Microsoft Visual Studio compatible output, which doesn't look like they have done. But it might be something nice to have. If other people would like this, maybe we should file this. What is this magic one line of code for making a window in Windows? All right. Let me finish this first. Alright, so let's just say that for now it's good enough. If you make an error, at least we have an error and we see the error, and then we will figure it out later. I'm not, I guess I don't care about parallel builds for now. I guess this is good enough for now. So yeah, this basically completes the process. The shaders are still here, but I want to keep them here for now, the binary shaders. But this makes sure that, oh, yeah, okay. This makes sure that, yeah, that we can just change the shaders, everything just works. Now it will be easier for us to write code, especially shader code. All right, a final quick thing I wanted to do is I wanted to support swapchain resize. But it might be too late to do that. Although, I mean, I should be able to get there. All right, let me quickly throw together a swapchain resize thingy, and then we can end the stream, and then I'll answer the single line window question. And then that'll be it. And then, you know, next time we will actually start rendering meshes, assuming that RTX arrives and things work. So we kind of were doing things in a very ghetto way. I want to do things in a bit less ghetto way. Let me first, you know what, before I break everything, I would normally submit at the end of my stream, but we've done like good stuff. So let's just submit everything that we have done. Day 3, checkpoint, let's say, well, whatever. Validation, cleanup, and maybe swapchain resize. So we have fixed all validation errors and have added Visual Studio driven shader builds. Yay. Oh, and I keep forgetting to do things. All right, so one thing at a time. Very quickly, I'm gonna check my validation stuff, which is gonna be wrong. Present. Yes, I wasn't doing this thing, which I knew I wasn't doing. Let me just, yeah. So without explaining this, because I don't know if I truly understand this. I used to understand this at some point, and then I stopped understanding this. So without saying why this stage should be that, I thought I got it wrong, but I wasn't quite sure. Yeah. Yes, we do that. All right. So now our code might be correct. Which I guess there was no validation error, but I think the thing that we were doing wasn't correct. There's a subtle reason why. I will like not explain this. Fix render pass begin to conform to Vulkan docs sync example. All right, so let's spend 5 minutes implementing swapchain resize, assuming we won't run into any weird issues, and then just end this. Or I mean like 10 minutes, let's say. So I want to start cleaning things up a bit. Let's just create a swapchain structure. Let's collect all of the state that we have used in the swapchain into this function. So we'll need a swapchain, and then we will need all of this stuff is good for now. We will need this. So it will be, oops, frame buffers, image views, images. It also will be width and height. Well, yeah. I don't think we need anything else for now. Yeah. So now let's just create a function that like create swapchain. Well, and I guess like bool create swapchain or something. And we already have a create swapchain function, if I remember right. But that's fine, we'll just overload this. So oops. All right, so let's just move the code that we were writing before into this function where all of this should go here. So we are getting, well, result key swapchain keychar swapchain image count images image count, oops, images, format, frame buffers, so width, height, we'll need a render pass. It's weird to pass it here. It's weird to pass it anywhere, but we need it. It's fine. It will be the last argument. So let's call it create or resize swapchain. Well, it's fine. Let's just call it create swapchain. And then we will so then we have created everything that we needed. Now we will use this function to both create function and like recreate function, so maybe we should call it recreate swapchain. So we need to destroy everything that we have just created from the old, well, attempt Alright, fine. You know what? Destroy swapchain result. Well, it's not really a result, it's like swapchain. So we need some of this code essentially. For convenience, I'll just add image count here. It's kind of redundant because these arrays are all this size, but that's fine. Swapchain. Why is my mouse cursor? Okay. Image views, so we can destroy the swapchain now. That's good. We can create the swapchain now. And now let's fill this stuff in. Oh, it's not, it's result. Frame buffers. So yeah, this is like just code refactoring, right? It's just moving things around a bit. Width is width. Height is height. Height. And then image count is image count, of course. I don't know if the frame buffer stuff survives because when we do let's be nice and let's handle the error at least in one place. So we can create the swapchain, we can destroy the swapchain now. We will pass in an optional argument here, which is like old swapchain. I'm not explaining any of this because I'm kind of out of time, because I kind of want to end the stream. But this is just when you create a swapchain in Vulkan. You can specify the old object, and then in theory it may reuse some of the resources, which is what you should do when you recreate a swapchain. Oh, why am I even doing this? Right, so I want to support window resizing, and the swapchain has a window size baked in it. So we can create a swapchain, we can destroy a swapchain, and then let's add a function that's like resize swapchain, that unfortunately has to have basically all of the arguments of this guy. And we'll just say void. Why are we even doing error handling here? I don't know. You know what? This is like not in the spirit of this stream. Let's just say that functions like this never fail. Like, it's super unclear how to handle failures in some of these functions. So what we need to do here is we need to grab the old swapchain from result swapchain, then we'll need to destroy, we'll need to do we need to destroy? You should need to destroy it, right? I don't, okay, I don't know actually. Oh, this should be called resize swapchain. So we'll create the swapchain, device, surface, caps, family index, format, width, I said, height, render pass, and then old swapchain. And then we will destroy the old one. Oh, jeez. Oh Oh no. Damn it. All right. Okay, you know what? Let's just get this code to run. All right. So, yeah, we need to create a new swap chain, and we need to create a new one to destroy the old one. And we also kind of need, like here or somewhere like this, device wait for idle. Because what if you're rendering into the swap chain right now, into the old one? What do you do, right? Alright, and now we do need to call this function. So let's replace the swap chain creation and destruction first. So we have a swap chain object now. Whenever we were creating it before, we don't need to create it there. We just need to create it here. Device, surface caps, family, index, surface, format, window width, I think, window height, and that's it. Oh, and like swap chain is the output object. We don't need this code. This doesn't compile. Why? Oh, swap chain format. Still doesn't compile. Why? Swap chain, device, surface. This is the problem with overloading. I should not have overloaded this function. Right, we need a render pass. But the reason why I don't care about overloading this function is because we will handle this later. We will like move this code to another file now, if it works. Swap chain, don't need this anymore. And then I just need to call it like this and like this. So this is just like, I'm not doing anything interesting, right? I'm just moving code around. Swap chain. All right. Let's see if that works. I said we'll need 10 minutes and we already have 12, so that works. Obviously resizing does nothing. Now we need to figure out the resize problem. The first thing is we'll, instead of window width, we'll just use swap chain width all the time. And instead of window height, we'll use swap chain height all the time. Alright, now when we do a GLFW loop, we should ask, do we need to resize the swap chain? To do this, you can do get physical device surface oh, it's the same capabilities function, I think, that we were just using before. It's the same thing actually. It's unfortunate that let's do current surface caps. You know what? Let's just, we could use GLFW width for this. I guess, yeah, let's just do this. Let's just say that we have a new window width and new window height. It's not awesome, but it's good enough for now. And then if new window width isn't equal to window width, we will use swap chain width. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, we will use swap chain height. And then if new window width isn't equal to window width, or new window height isn't equal to window height, then we need to store these. Oops, and we need to resize swapchain. And resize swapchain is the same call as create swapchain, more or less, so, or basically the same, right? So we'll just do that. And maybe this works. So the idea is when the window changes, this guy will destroy the old swapchain, create a new swapchain, reinitialize all of the frame buffers and image views and images and everything that we have ever created. And then things hopefully just work unless we didn't do something right. Well, we clearly didn't do something right. Oh, we are... Okay, wait. Let's do this. It probably still doesn't work. Alright, so we clearly didn't do something. Current extent, min image extent. Oh. Do you have to do something to GLFW for window resize to? No. How? Interesting. Yeah, okay, so the more correct thing to do this, which is what I wanted to do at first, and then I decided I shouldn't, and then I decided I should. But the more correct, well, the sort of correct thing to do, at least on Windows, on most systems, is the correct thing to do is this. Let's just shadow these variables. So when you ask what's the capabilities of the surface, it gives you current extent, which is the current size of the surface that you should be using. And if you're not using this size, then weird things might happen. So the correct thing, the more correct thing, is to ask if this is different from current extent width, or swapchain height is different from current extent height. Then resize it with surface caps current extent width, surface caps current extent height. And we can actually be nice and move this guy to a function if necessary. So let's just modify this function. Let's return the width and height, and then resize, and then just move this code to there. And then we will say that we'll need a physical device as well, but what can you do? And then we'll say that if the size is already equal, then we'll just return. Otherwise, we need to do the same thing that we were doing before. Well, but the problem is that this will not work. The problem is that for some reason, as far as I understand, oh, is no. Well, okay, you know what? Just like. It's slightly weird because we're now like getting this thing twice. But that's fine. So this will not work. Or rather, it will not resize anything, right? Oh, it will. Okay, damn it. Alright, fine. I'm slightly surprised that... Oh, this is because the validation layers never update the internal state if you never call this function again. And we never called this function again. I see. Alright. So the good news is our code works. The bad news is that during a resize, weird things happen. We are not going to be solving this right now for sure. I don't even know if this is solvable. So it would be a bad thing to try to solve this problem now. I also am not super sure. This is like slightly weird because we are passing the old swapchain into the create swapchain function, but we are not deleting it. But alright, anyway, so things seem to work. We have implemented everything that I thought we had to implement today, which is good because next time we can focus on rendering something that's more interesting than a triangle on screen. I kind of want to make sure that the fact that we are removing the old swapchain is fine. Oh. To still present. Old swapchain is retired, even if the creation fails. What does retired mean? Oh, right, yeah, so the application can destroy all swapchain. It doesn't say if it should. It doesn't say that it should. So it might be possible to implement like seamless resize of window in Vulkan, but it might be complicated. We are definitely not going to try. For one, we are not even getting this loop right now isn't called. Oh, well, I guess we are okay, wait, so we are doing this, which like breaks some things. The image might pause right now. Well, it's the same thing. All right. But yes, it might be possible to implement a seamless window resize on Windows and Vulkan. It might be impossible, it might be really hard, it might not work on Intel drivers, who knows? We don't care. What we care about is we have a triangle, the triangle can be resized now, so we are done. So I guess that's it. So as I mentioned before, the next stream will be on Sunday, which is tomorrow. Unless something goes horribly wrong with my computer. In which case I might still do a stream, or I might just skip tomorrow in favor of actually getting a computer built, right? It depends on, I'll watch the stream, so I don't know if the video encoding change that I did for hardware encoding fixed the stream freezing problem. If it did, then it's fine, I can just do another day from Surface Pro. And if it didn't, then I kind of would like to just build a new computer. So we will see. But most likely the next stream will be tomorrow, same time, 10 a.m. Pacific time. So now let's cover the question of magic one-line code to create a window in Windows. So I have this guessed that I should really just publish as a GitHub project, because I search for this very frequently. Which is like the shortest possible way. So right now what we have written is not the shortest possible way to render triangle in Vulkan, but you know, it's like reasonably close. It's not too, well, it's like 700 lines of code, right? It does support GPU selection, does support window resize, but it's pretty minimal. Like, we aren't doing things that are that long that we don't have to do, because you have to pick a GPU. We don't have to pick a dedicated GPU, but you have to pick a GPU that has presentation working. And okay, you don't have to enable debug layers, but you know, that's like a small thing. Oh, we should, right now our program probably crashes in release, so we should fix that. But anyway, so it's pretty minimal. So I had a thing where it will be impossible for me to find. All right, let's try Google search. Guests, Zug, CG, GitHub, Nano, GLFW. Yeah, GitHub is really nice. The non-nice thing is that, oh, okay. I was gonna say the non-nice thing is that search usually doesn't work, but the search does work. So this is a minimal hello world on Windows in OpenGL 1.1, 41 lines of code. I mean, you might be able to remove one line. I mean, there's like lines with spaces, right? You don't have to have them. But this is the amount of code that you need for OpenGL 1.1. This is crucial for OpenGL 2.0. Well, for OpenGL like 3.0 or something, core profile, you need like way more code than this. Less code than Vulkan, but way more code than this. But this is the minimal program. Let's look at this just for fun, right? So, okay, this is the single line create window that I was talking about. The thing that this code is doing is it's picking a built-in Windows window class called listbox. I forget why listbox works well or better than other. There's like a few other classes, but this is like less weird than other ones. And yeah, so it just creates a window in like one line of code, and then it gets the DC, which you need in Windows to present to this DC. You need this in Windows to create an OpenGL context, because the GL context has to be like bound to a DC or something. I don't know. So then we do the set pixel format, choose pixel format. There's no error handling there. But yeah, it's like a double buffered context with 32 bits per pixel. Activate OpenGL context, create and activate. Show window. Unfortunately, by default, the windows are hidden, I think. So you have to do that. And then there's your message loop. This handles the quit message, I think. Maybe, I want to say. Standard message loop, get client rec. This is your like swap chain, height, width, viewport, clear, and then triangle. I mean, you might be able to, well, I mean, this is basically, this triangle is like more interesting than our triangle, because this has colors and vertices and ours doesn't present. That's it. So yeah, let's paste this code here and then run that instead. Oops. So let's run our OpenGL triangle. All right. It supports window resizing, obviously. It's also non-smooth, right? Oh, this is the list box, by the way. I don't know if you can see this. I hope you can. But right now, if the stream hasn't paused, in the top, like the top line is like a list box. But when you render, it doesn't show up, so it's fine. Yeah, so that's like a triangle in OpenGL 1.1, right? So that's 40 lines of code, so that's like more than 10x fewer lines of code. So that's unfortunate, but hey, you can't do a lot of nice things in OpenGL 1.1, so it's not, we shouldn't feel that bummed about the fact that the program could be much shorter, I guess. I don't know, maybe we should be. So yeah, that was the single line window creation, and then like 40 lines of code for an OpenGL program, for a complete OpenGL program. So this is the 3 swap chain resize. We can now resize the window. There's a couple of things that I haven't covered with respect to swapchain resize that you might want to do for a full-fledged program, but it probably is fine. Oh, I wonder, so the thing is, we are using glfw right now, and I don't plan to stop using glfw, because if anyone ever wants to run this thing on Mac or Linux, it probably won't run on Mac. Today it will run on Mac, but it might run on Linux if you fix some code long term, right? Long term it might not run on Mac because we'll start using like hardcore extensions that MoltenVK doesn't support. So yeah, but we didn't have to use glfw. We could have used this like single line window created using, you know, magic window, and that would probably have worked just fine. Let's try this just out of curiosity. So basically there's no window anymore. There is a an HWin that we pass. Our code starts becoming non-cross-platform, right? Oh, and we need to do show window. I don't think we need to do this, because this should only, or maybe we do. No, yeah, I don't think, yeah, you shouldn't need to do this. This should be fine. So we can't get the window size like this, but we can get a window size like this. Int window width. In fact, we don't even need this code. We should have been using... Oh, we aren't... Are we using these guys anymore? We sort of are. Alright, that's fine. Yeah, so rect right minus rect left, int window height rect top minus rect bottom. And then we need the message loop, which is like these lines, right? So there's that, and we don't need this, and we don't need glfw init. In fact, we just don't need glfw, we just include Windows H. We'll just not destroy the window, because who cares? Windows will clean up. We need a message object, or what's it called? MSG. And we might have a window without glfw with Vulkan. Well, okay. We clearly don't. Intel driver doesn't like... Yeah, Intel driver doesn't like our window. Alright, whatever. We don't have a window without glfw. This is like, OpenGL works in it. I don't know why Vulkan doesn't, but we might not be doing something that's like important. Like maybe you do need some of this stuff. I thought you don't. Or maybe listbox just does not work with Vulkan, but does work with OpenGL 1.1. Whatever the case may be. Oh, also, it could have been that it's just release mode. No. Alright, that's fine. But yeah, that's kind of it. So we spent all this time to write something that's 40 lines of code with OpenGL 1.1, but the good news is we have access to way more functionality now than you do in OpenGL 1.1. How do we even run and release if this function should not have worked? How do we have a debug report callback? Well, debugging and release is not fun. This is slightly sketchy, it should not have worked. But okay, whatever, we'll figure it out next time. Alright, yeah, that's kind of it. Thank you for being on the stream. Next stream, unless something horrible happens to my computer, will be tomorrow, 10 AM Pacific time, where we will render a mesh. and then like fix anything that we haven't fixed today. I think we fixed everything that we wanted to. All right, thank you. Stop streaming.